Okay, so let us discuss about the optimum design of the damped absorbers. Okay. So in this section, we are going to consider the damped absorber applied to an undamped single degree of freedom system. So these are applied to undamped single degree of freedom system. Okay, and in this case, we will first take up the general principle of the optimization procedure when the damping is present in the secondary system, and we consider the damping is to be represented by the complex stiffness, and then we will find out the specific results for the various types of the damping. So first what we are going to do, we are going to apply the general principle of the optimization procedure whenever the damping is present. Damping is present in secondary system, and that is represented by what? That is represented by the complex stiffness, and then we can go for the results for the various types of the damping. So we will obtain the results for various types of damping. Okay. So let us first understand the undamped primary system under the harmonic force excitation and the undamped primary system under the harmonic base excitation. Okay. So first I will draw this system with the, this is stiffness K1 which is attached to a mass M1. Right. Then let us consider the displacement of it is x1 bar, which is dependent upon the x1 bar e raised to j omega t. So this is small x1 bar is equals to x1 bar e raised to j omega t. Now the secondary system is having the complex stiffness. So let us consider this the spring having the stiffness K2 star, and at the end of it the mass M2 is attached, right? Let us consider the displacement of this mass as x2, and it is x2 e raised to j omega t. So this is a undamped absorber, figure A, undamped absorber for primary system under harmonic force excitation. Okay. Now what is the difference between this system under harmonic force excitation and the base excitation? We can see that the harmonic force excitation, the support is fixed, right? And in this case we can show the transmitted force, let us say it is denoted by ft. So it will be ft e raised to j omega t, right? So this is a transmitting force acting in the downward direction from the support like this. And let us consider the force which is acting on the mass, right? So let us, it is denoted by F e raised to j omega t. Okay, so this is the component of force acting on the mass. Okay, now let us draw a system having the damped absorber. I have written undamped actually, so it is should be a damped absorber. So it is a damped absorber for primary system under harmonic force excitation. And let us now consider the damped absorbers for primary system under base excitation. So in this, we consider the base is moving with x equals to x bar e raised to j omega t. Let us x1 be the spring stiffness. Let us consider the mass m is attached to it, having a displacement x1 bar equals to x1 e raised to j omega t. Then to this again a complex stiffness spring having a stiffness K2 star is attached, and to this mass M2 is attached. Okay, let us consider the x2 bar is equals to x bar e raised to j omega t. Okay, so this is a system under the base excitation. Okay, so you can see that the base is getting excited in this case. Okay, now what we wanted to study in this case, we wanted to study the transmissibility. Okay, so let us consider the undamped single degree of freedom system. Transmissibility we wanted to study. Okay, so let us consider the undamped single degree of freedom system subjected to harmonic force or base excitation, which is shown by a which is shown by dotted lines. Sorry, which is shown by solid lines, right? So in this case, you can see this. This is a system with a damped absorber for primary system under harmonic force excitation, and this is a system which having a damped absorber for primary system under harmonic force under the base excitation. And in both the cases you can see that there is no damper, so it is also can be called as damped absorber for undamped primary system. Damped absorber for undamped primary system, right? So we can write it down here word as undamped. So damped absorber for undamped primary system under harmonic force excitation is this, and base excitation is this. Okay, now in both the cases the solid lines can be seen for this part figure. So if I highlight it by a different line, right, so this part you can say that this is shown by a solid line, and this is part which is shown by a solid line, correct, as shown in figure A and B. Okay, now the stiffness and mass of the system are respectively represented as K1 is the stiffness and M1 is the mass, correct, and it is desired to design a damped absorber which is shown in figure by dashed lines. So what we wanted to have the design of a damped absorber which is shown here by dotted lines. So what is the dotted lines indicate? If you look at closely, this dotted line indicates a spring with a K2 star, that is a complex stiffness, and the mass M2 is attached to it. So these are connected by the dotted lines. Similarly, for the system under the base excitation, you can see this. This is a K2 star, which is the complex stiffness for the spring, and mass M2 is attached to it. Okay. So in this case, what we wanted to find out, what are the maximum values of the transmissibility. So the maximum values of transmissibility is the minimum in the entire range, that is from 0 to infinity. And what we wanted to design a damped absorber in such a way that the maximum value of the transmissibility is minimum in the entire range, that is from 0 to the infinity. So we wanted to have the maximum transmissibility whenever the frequency range is 0 to infinity. Okay. In this way, we are going to design this, the values of the K2 star and the M2. Okay. What is this K2 star? It is a complex stiffness, and mass is the damped absorber mass, that is denoted by M2. So now we can have the equations T. T is equals to Ft by F, that is for the figure A, that is the case of a force excitation, right? And T is equals to x1 bar by mod x. This is the equation for base excitation. Okay. Now we can see that these are identical, and these are identical in nature. So we should note that, and to which these are identical, as this transmissibility values are depending on the first case to the force transmissibility, and the second case it is depending upon the displacement transmissibility. So the notations here being explained earlier, the same notations are shown here, right? And we should know that the transmissibility expression represents the, this expression A, this represents the response of primary system, since we know that x1 bar is equals to ft by k, right? So we can write it down here it as ft by k1. So what is this x1? X1 is the displacement of the mass 1, and we can write it down the displacement of the mass 1 x1 as ft by k1, because we know that force is equals to k into x. So by just rearranging these terms, we can find out what is the, this x1, which is nothing but the displacement of this mass 1, which is proportionate to the transmitted force Ft divided by the stiffness K1 of the primary system. Okay. Now we will analyze only the system shown in the figure B. So we now analyze system shown in figure B, that is the system corresponding to the base excitation. And we will be obtaining conclusions that will equally valid for the system shown in the figure A, right? So we will obtain the derivations or the expressions for the second case, that is this case, and we can show that this will be equally valid for the force excited system, that is for this system. Okay. Now let us consider the different parameters which are required in the design of the damped absorber. So the design of damped absorber involves three parameters. Which are the three parameters involves? The first is mass M2. The second is stiffness represented by real part of K2. Now why we are saying here the real part of K2? Because K2 is a complex stiffness. So first we will consider the real part of K2, and the third component is involving the stiffness represented by the imaginary part, or we can say that the damping represented by the imaginary part of K2. So we'll now consider the damping which is represented by imaginary part of K2. Okay, and let us define some of the parameters. First parameter we define is the non-dimensional ratio. Non-dimensional mass ratio, that is M2 by M1. Let us call this M2 by M1 as mu, and this is called as inertia parameter, or it defines the inertia parameters. Now let us consider the second parameter in the design. The second is stiffness parameter. Stiffness parameter can be expressed in terms of non-dimensional tuning ratio. Now what do you mean by non-dimensional tuning ratio? It is the ratio of frequencies. It is denoted by nu, and what is nu? Nu is equals to omega A divided by omega 0. Whereas what is omega A? Omega A is equals to K2A divided by M2 raised to half. Whereas what is K2A? K2A is the stiffness of absorber at frequency omega A. And what is omega O? Omega O is nothing but obtained from the stiffness 1 and mass of the absorbers, that is primary and the secondary mass. So this K1 divided by M1 M2 raised to half. So this is called as omega O, and this omega O is also known as the lock frequency with which, or we can also call it as the natural frequency of combined system when absorber mass is rigidly connected to 1, or mass 1, rigidly connected to mass m1. So we can see that This stiffness parameter is expressed in terms of non-dimensional tuning ratio. And what is this non-dimensional tuning ratio? Nu. Okay. And what is nu? Nu is the ratio of omega A divided by omega O. Whereas what is omega A? Omega A is the ratio of K2A divided by M2 raised to half, right? So it is the square root of K2A by M2, right? Whereas what is K2A? It is the stiffness of absorber at frequency omega A. And what is omega O? It is the K1 divided by M1 plus M2 raised to half. And this omega O also known as lock frequency, okay, which is nothing but a natural frequency of the combined system when the absorber mass is rigidly connected to the mass M1, right? So we are assuming that absorber mass M2 is rigidly connected to the mass M1. Look at the diagrams again. In this diagram, we can say that this mass M2 is rigidly connected to the mass M1. So we can obtain the frequency omega O, which is dependent upon the M1 and M2 and the K1. Okay. Now let us look at the third parameter. The third parameter of the system is called as damping parameter. It is denoted by non-dimensional loss factor. Now in the MCQs I have shared you might have find out the different MCQs which were based on this loss factor. Now you will be able to solve those numericals also, MCQs also, which were based on the loss factor. How do they denote? They are denoted by eta 2 omega, and that is equals to K2I star, which is dependent upon omega, divided by K2R star, which is also dependent upon the omega. Okay. Whereas what are the subscript I and R denotes? Subscripts I and R indicating the imaginary and real parts. Okay. So we have the damping parameter to be expressed in terms of non-dimensional loss factors. So N2 omega equals to K2I star omega divided by K2R star omega, right? And I and R is nothing but imaginary and real parts. And the fourth part, this is called as the forcing frequencies. Forcing frequency. It is again expressed in a non-dimensional, non-dimensionalized parameter as the excitation frequency to the excitation frequency ratio, or we can say that it is the ratio of omega by omega 0, and it is expressed in terms of this omega. Okay. So these are the four different parameters we need to remember. Which are the first? The first is this nu, this, right? This mu is the inertia parameter. Okay. The second, nu is the stiffness parameter, right? The third that we need to remember is a damping parameter, which is also known as non-dimensional loss parameter, N2 omega. And the fourth, that is the forcing frequency parameter, which is a non-dimensional or non-dimensionalized as excitation frequency ratio, and this omega is omega by omega 0. Okay. Now let's look at further how we can connect these two. So we know that or we can find out that generalized the absorber system. We have generalized the absorber system so that we have generalized the absorber system so that both its stiffness and loss factor. What is the loss factor? We have defined it as, I am rewriting here, N2 omega are frequency dependent. So what is the meaning of this statement? So we have generalized the absorber system such that it will have the stiffness as well as the loss factor. Now, on which factor this loss factor depends upon? This loss factor is basically dependent upon the stiffness of the secondary spring, right? That is the K2. But we know that it is not a simple spring, it is a spring with a complex stiffness. So it is indirectly dependent upon what? Loss factor, and loss factor is directly dependent upon what? The ratio of imaginary stiffness and the real part of the stiffness. Okay. And now of the three absorber parameters, the mass ratio, that is, what is the mass ratio? Mu, and this mu is equals to m2 by m1, correct? Mass ratio is selected on the basis that absorber deformation does not exceed the acceptable limit. Does not exceed the acceptable limit, and further, what is the, we are doing the overall increase in the system mass and overall increase in the system mass is within the desirable range. Okay, so what we are doing, of the absorber parameters, right? We are selecting the mass ratio on the basis of the absorber deformation that does not exceed that wait hang, does not exceed the acceptable limits. Okay, and overall increase in the system mass lies within the desirable range. Okay, and the absorber deformation is expressed in terms of non-dimensional relative transmissibility. And how it is expressed? This non-dimensional relative transmissibility TR is expressed as mod of x2 minus x1 bar divided by x bar. What is this x2 bar and x bar? X2 bar is the displacement magnitude for the secondary mass. X1 is the displacement amplitude for the first mass, and x bar is the amplitude for the base, right? So now from this, sorry, we determine the optimum values of nu. What is nu? It is a tuning ratio, right? It is a non-dimensional tuning ratio, and we know that this nu is dependent upon omega A and omega O, right? And determine the optimum values of nu and n2 omega. Okay, what is this n2 omega? N2 omega we know that it is a non-dimensional loss factor, correct? On which factor this again I am repeating for you. It is depending upon n2 omega is equals to k2 I star omega divided by k2 r star omega. Okay, so we are determining the optimum values of nu and n2 omega, that is loss factor, okay, for a given, that is prescribed, or we can say the prescribed values of mu. And we know that what is mu? Mu is equals to m2 by m1 with objective of minimizing Tmax in the entire range of omega. What do you mean by this Tmax? Tmax is the transmissibility, right? So we wanted to minimize the transmissibility in the entire range of the omega. And what is this omega? Omega is equals to omega by omega 0, right? So it is the ratio of the excitation frequencies. Now we can write it down the equations as, so the equations of motion for two masses, we can write it down from the figure m1 x1 double dot plus k1 into x1 bar minus x bar plus k2 star is the stiffness, and it is connected to the x1 and x2 equals to 0, right? This we have written considering the first mass. Look at this. So for this system we have written m1 x1 double dot, right? m1 x1 double dot plus k1 into x1 minus x plus k2 star into x1 minus x2 equals to 0. Now we will write it down for the mass 2, right? So first parameter is the inertia parameter, and the second parameter we are going to write down is only the stiffness parameter considering the spring 2 only. Okay, so we write down, let us call this expression as 1. So we have m2 x2 bar double dot plus k2 star into we will write down the x2 part first, right? As we are considering the displacement corresponding to the mass 2 minus x1 bar equals to 0. Okay. Now we know that what is the x1, x2. So substituting this small x1 bar as x1 bar e raised to j omega t, right? x2 bar as x2 e raised to j omega t, and x bar as capital X bar e raised to j omega t in the above two equations. So what we are going to get, look at this. If we differentiate this twice, so what we are going to get, x1 double bar is equals to x1 bar into omega square, right? And this e raised to j omega t will be as it is, but what we are going to get, we are going to get here minus sign because it is a complex, correct? So we will get here minus sign. Similarly, x2 bar will be also having the minus sign x2 omega square into e raised to j omega t, and here also we are going to get. Okay. So what we are going to get after replacing these three, 1, 2 and 3 in the equation 1 and the equation 2. Look at, so we will write it down, m1 into what is x1 bar? It is minus of x1 into omega square e raised to j omega t. So we can replace it as minus of x1 bar omega square e raised to j omega t, right? Plus k1 into what is x1? It is x1 bar e raised to j omega t. What is x bar? X bar e raised to j omega t plus k2 star into bracket. What is x1? Again, this is x bar e raised to j omega t. Then minus x2 bar. So here we have a minus x2 bar. So this minus x2 bar will get replaced by this, right? So we will have minus x2 bar e raised to j omega 2 equals to 0. Now, if you look at closely, each term has the term e raised to j omega t. So we can cancel out this term, which is common in both all the terms. So this we get cancel out. Okay. Now, if we simplify, what we are going to get, taking the terms having the x1 common, right, and k2 common, and keeping the x as separate, keeping the x bar separate, keeping the x1 separate, and keeping the k star separate. Okay, so we will have, look at this term is k1 x1, right? Then this is also a term with the k1, this is a term with the x1, right? So we will add these two terms and we will take the positive sign first. So we will get x1 bar into bracket, this is k1 minus this m1 omega square. Okay, we get this term. Then what is remaining? This x bar term we will transfer it on the right side and then we will combine these two. So plus K2 star into bracket x1 bar minus x2 bar, and this will be equals to K1 x bar. Let us call this expression as 3. Okay, and from the expression this, what we are going to obtain, x2 bar can be written as minus of x2 bar into omega square e raised to j omega t. So we'll replace that. So now we write it down, it as m2 into minus of x2 bar omega square e raised to j omega t plus k2 star into bracket, for x1 we are writing down x1 e raised to j omega t, for x2 we are writing down x2 bar e raised to j omega t and equals to 0, right? So now we cancel out this, a term which is common to the all three, and after simplification what we will transmit, we will transmit this k2 star on the right side and we will combine this x2 term together. Okay, so we write it down this as k2 star minus m2 omega square into x2 bar. Look at this, this is the x2 bar and this is x2 bar. So this k2 star into x2 bar is also having a negative. So here it is having a negative sign, hmm, and this is also having a negative sign. I think I have written reverse. This should have the negative sign x2 and this should be 1. Okay, because what is the original equation? We have it is x2 minus x1. Okay, so x2 is early first and then we will get the x1. Okay, so we will get k2 star minus m2 omega square into x2 is equals to k2 star into x1 bar. So let us call this expression as 4. Earlier was the expression 3. Now by solving these two expressions, what we will obtain? We will obtain the solution of these two equations, that is the equation 3 and 4. So I am writing down the solutions of equation 3 and equation 4. So how we can solve these two expressions? Look at this, in the expression 4 we have x2 bar and x1 bar, right? And in the expression 3 we have this x1 bar, k2 star and the k1x. Okay, so what we can do, we can obtain the value of the x1 bar and x2 bar from the expression 4 and substitute this value in the expression 3 to get the value of x1 bar by x. We write down the x1 bar by x as k1 into k2 star minus m2 omega square which is divided by k1 minus m1 omega square into k2 star minus m2 omega square minus k2 star into m2 omega square. This is the expression we obtain by solving the expression 3 and 4. Now it may seems to be beyond the scope that how to solve this, but how we can obtain, I am just telling you the procedure. From the expression 4 we can get the value of x1 by x, x1 by x2, right? or we can obtain the x1 in the form of x2, that is k2 star by k2 star minus m2 omega square into x2 bar divided by k2. This value we can substitute in this expression, right? So we will have this expression in the form of this x1 will get replaced, right? So x1 will get replaced by this term involving this, correct? And then we can obtain this x2 here. Here we have k2 star. This x1 needs to be also replaced. So this x1 will also get replaced by this, right? And then by solving for the x2 bar by x, we can obtain the this value. That is x1 bar by x I have written first. Then in the same way we can also get it for x2 bar by x. x2 bar by x bar as k1 into k2 star divided by k1 minus m1 omega square into k2 star minus m2 omega square minus k2 star into m2 omega square. Now let us call this expression as 6 and this expression as 5. Okay. Now if you closely look at the denominator in this expression x1 bar by x, k1 minus m1 omega square, k2 star minus m2 omega square minus k2 star m2 omega square is same here also, which is the ratio of the which is the denominator of the ratio of x2 bar by x bar. So here also we get the same. So from this expression, that is expression 5 and 6, using equations 5 and 6, what we obtain? We obtain the x2 bar minus x1 bar by x bar as k1 m2 omega square, and the denominator will be as it is. What is the denominator we have? This k1 minus m1 omega square into k2 star minus m2 omega 2 square minus k2 star m2 omega square. Okay, this we get. So we write down here, we write k2 star is equals to k2 omega into bracket 1 plus j and 2 omega, right? Where r is the drop subscript. What do you mean by this? K2 omega. We have earlier obtained that the K2 omega is the expression of the stiffness, and if we drop these two subscript, that is R and the I, what we are going to get? We are going to get the R indicating the real part of the stiffness, whereas I indicates the imaginary part of the stiffness. And here we have dropped the subscript R and we have replaced this subscript by omega. So what it refers? It refers that it is the value obtained at frequency omega. So this K2 is the value which is obtained referring to the frequency omega. And now using non-dimensional parameters, non-dimensional parameters, The transmissibility obtained from equation 2 and equation 5, that is this expression 5, what we get, equation 2 and equation 5, after multiplying throughout by nu square divided by k1 k2 omega. K1 k2 omega. What we can write it down. It is written in the form of this nr plus jni upon dr plus jdi. Whereas what is this nr? Nr is the real part of numerator, and what is it? It is equals to nu square minus omega square into alpha. And we have obtained what is this omega? Omega we have defined as the excitation frequency ratio, right? So we know that what is omega? Omega is equals to omega by omega 0, right? This is the real part of the numerator, whereas what is ni? It is the imaginary part of numerator. It is equals to nu square into n2 omega. We know that what is this n2 omega? It is a non-dimensional loss factor, right? And it is depending upon the k2 I star omega by k2 r star omega. Right here again I am writing down what is this n2 omega. It is a ratio of k2 I star omega divided by k2 r star, which is dependent upon the omega. Okay. Now let us define what is this dr. So dr is equals to real part of denominator. What is that real part of denominator? It is equals to 1 divided by 1 plus mu into omega raised to 4 into alpha minus omega square into nu square plus alpha plus nu square. Let us call it this expression as expression, sorry, this was 6. Let us call this as 7. Let us call it this as 8. Let us call it this as 9. Let us call it this as 10. Let us call it this as 11. Okay. So real part of denominator is 1 upon 1 by 1 upon 1 plus mu into omega raised to 4 alpha minus omega square into bracket nu square plus alpha plus u square, and di is imaginary part of denominator So that is equals to V square and 2 omega 1 minus nu square. Let us call this expression as 12. With what is this alpha in this case? With alpha is equals to K2A divided by K2 omega. Okay. Now, similarly, we can get the values of the transmissibility for the expressions of transmissibility for we can get transmissibility for equation TR is equals to x2 bar minus x1 bar by x bar, and this x2 bar minus x1 bar by x bar, that is equals to k1 m1 omega square divided by k1 minus m1 omega square into k2 star minus m2 omega square. That is earlier equation that we have written, k2 star into m2 omega square. For these two, we can also write down the t. This equation was numbered as, I will show you what was it was numbered. This expression 7, and this expression, I think it was written as expression 3. So from the 3 and 7, we can write it down t as pi square alpha divided by dr plus jdi. Okay, and let us call it this expression as 13. Now, sometimes you may find out a lot of difficulties in solving those equations, because in this book of Malik and Chatterjee, they have skipped so many steps and directly they arrived at the equation that we are unable to get. And even sometimes you may find out it difficult to by heart, right? But there is no option, because solving those equation may be cumbersome. Sometimes if the terms may be less, you can solve. Otherwise, you will have to do it as by heart. Okay. Any questions from your side? Yes.
No, sir, not yet.
Okay. Okay. Yes, you have written the same that many steps have been skipped. Okay. Now let us discuss about the absorbers with ideal spring. Before we proceed towards the absorbers with ideal springs and viscous dashboard, which is a topic which is mentioned, let us discuss what do you mean by optimum tuning and damping. Optimum tuning and damping. Now, Before we find out what are the optimum values of the mu and the damping, that is optimum values of nu and n2 omega. There are two values of omega, right? Besides omega equals to 0 and transmissibility equals to 1, for which T is independent of and 2 omega. Okay, and these values are called fixed point frequencies, and these are obtained using, and these are obtained as follows. So what is said here, for obtaining the optimum values of the nu and n2 omega, let us find out the different values of the omega for which the t is independent of the n2 omega. So apart from the omega equals to 0 and the t equals to 1, and the values which we are going to get for the omega are also referred as fixed point frequencies. Okay, so find out those values. I am writing down the equation. T square is equals to v raised to 4 into bracket, not, it is not v, it is a nu raised to 4 into bracket 1 minus omega square alpha divided by nu square bracket square plus n2 omega square divided by so we are dividing it by nu square, nu raised to 4 1 minus omega square bracket square into 1 upon 1 plus mu omega raised to 4 alpha minus omega square into nu square plus alpha plus nu square whole divided by nu square into 1 minus omega square, this whole raised to square plus n2 omega square. Now for you to remember this, you need to be a superwoman. Even not easy for even me to remember this. But they have mentioned these two equations to get the values of t square. From this expression, what is they have mentioned, we can see that t square becomes independent of the n2 omega if the terms involving this curly bracket, which are the curly bracket, this is the first curly bracket and this is a bottom curly bracket. I will write down this in a piece of paper because it is very difficult to write down here. If the terms involving in the curly bracket, that is in the numerator and denominator are the same, that is when the 1 minus omega square alpha upon nu square is equals to 1 upon 1 plus mu, that is this term, omega raised to 4 alpha minus omega square into nu square plus alpha plus v square divided by nu square into 1 minus omega square, and this whole again raised to 2. Okay, so the t square will become independent of the n2 square omega or n2 omega when the term which is involving in the numerator's curly bracket and this will become same. Okay, so further solving, how can I do? I need to create a new jam. So by simplification of that term, so we obtain b square minus v square minus omega square alpha equals to plus or minus 1 upon 1 plus mu omega raised to 4 alpha minus omega square into nu square plus alpha plus nu square whole divided by 1 minus omega square. So we have eliminated the square in this case, and now by taking only the positive sign, by taking only the positive sign, what we obtain? We obtain nu omega raised to 4 alpha equals to 0, that is omega equals to 0 as nu 0 and alpha 0, right? So what it will become, satisfying the trivial static situation when t is equals to 1 and the damping has no role to play, and considering the negative sign on the right hand side of the equation that was shown earlier, that is using this expression, that is the negative side on the expression, we can obtain nu plus 2 upon nu plus 1 into bracket omega square alpha minus 2 omega square into nu square plus alpha plus 2 v square equals to 0. So this is a equation which is called as biquadratic equation. Why it is called as biquadratic? Because it is having a term omega raised to 4. So this biquadratic equation will give us two roots, right? And which will give us two fixed point frequencies at which t is independent of n2 omega. Okay, so let us assume these two fixed point frequencies be phi omega a and omega b. Then this expression will become this. Let us call this expression as 1. Let us call this expression as 1. So we get omega a square plus omega b square equals to twice of nu square plus alpha into nu plus 1 divided by mu plus 2 into alpha. So this we get. And we can also have the alternate solution, and to get the alternate solution of the earlier expression, that is for this expression 1, what we can do, we can use the two extreme values, that is to get alternate solution of expression 1. We can get, or we can use extreme values. What are the extreme values that the n2 omega can have? One will be n2 will be equals to 0, and another n2 omega will be tends to infinity, right? That we can use in the main equation that we have solved or we have written, right? That was in the previous jam, right? And then what we can do, we can equate the two extreme values of t square by substituting these two. Okay, so let us call this value, we are getting it as t o square and t infinity square. So we get the two fixed point frequencies. So at a fixed point frequencies, we get t square is independent of n2 omega, and therefore we can get to, which is nothing but transmissibility at the n2 omega equals to 0 as plus or minus nu square minus omega square alpha divided by 1 upon 1 plus nu into omega raised to 4 alpha minus omega square into nu square plus alpha plus nu square. Let us call it this expression 2, and we will have t infinity as equals to plus or minus 1 divided by 1 minus nu square. So let us call this expression as 3. So we can see that how the TO and T infinity varies with the values of the omega. So we can find out the spatial situation with nu equals to 1 and alpha equals to 1, and then we can find out the variation of the x1 by x bar versus the omega for the given values of the alpha 1. And whenever we are writing down alpha as 1, which means that frequency independence of the absorber stiffness. So if I try to draw a graph, although it's very difficult to draw a graph on the board, sorry, I will not be able to. I will share this separately. Okay. So I think we should stop now, because to draw a graph on this Jamboard is very difficult. It requires a tab. So in the next session, we will going to study about the absorbers with the ideal springs and the viscous dashpots, and then gyroscopic vibration absorbers and the impact absorbers. I will tell you when it is possible for me to conduct the session. If in the week, if it is possible, I will let you know. Otherwise, we will take it on the Saturday, Sunday. Okay. Acha. Okay. Let me stop the recording. Then I will tell you.